All right, today we're going to be ranking every field in mathematics. This is a purely my personal opinion, so you can rank them afterwards. After this, I'm going to have a QR code. Yeah. So let's start. So these are what I'm going to rank today. So these are basically one of the most of them are well known. So it's pretty obvious that we're going to be ranking these today. We start with number theory, and number theory is the study of integers and their properties and relations. And some examples of what you do in number theory is primes, distribution of primes, arithmetic operations, so like your basic like primary maths, and then you have Diophantic or Diophane equations, which are just polynomial equations with integer coefficients. And you also have modular arithmetic, real with complex analysis, and fields, which all of these are number theory. And some of the famous theorems we see is Fermat's last theorem, which are proven like it's one of the biggest problem proven this century, so it's pretty significant. We got Goldbach conjecture, which is not proven yet, and you get like a couple $1 million if you prove that. You also got Riemann hypotheses and Galois theory, which are pretty significant when we look at analyzing how like polynomial equations work. There's some applications, basically most of cryptography, like your bank accounts and anything online uses number theory because primes are just so special. And you got pseudo random number generators, which are just what you use when you do like cryptography because you need a random number. But also sometimes in games or like computer graphics, they also need random number generators. Then this also links really nice into computer science and discrete maths. So in my opinion, I like number theory. So I'm gonna give it an S tier because it's one of my it's one of the most beautiful it's one of core it's the core of math. It's just numbers, right? Everyone learns about numbers when they're like 2 or something. Yeah, you learn like 1 + 1 = 2. But actually there's a lot more to see, to discover still in number theory, as we see a lot of conjectures not even solved. Right, next we got geometry. So geometry is just studying properties of space, such as distance, shape, and size. And there's a bunch of geometry here. Like Euclidean geometry is basically what you do, basically, until like university. You also got differential geometry, which is looking at geometry and calculus. It's a bit of mixture between geometry and calculus. You got non-Euclidean, which is elliptic and hyperbolic. Earth is a really good example of studying non-Euclidean geometry because Earth is not flat. Okay, no flat Earthers here. Okay, topology, right? Topology is just a more abstract view of geometry. It studies how space is connected and how compact is something. So it's rather than the distance, shape, or size of something, it's going to be about the general structure of a geometric object. And then lastly, we got a bunch of these: algebraic geometry, complex geometry, discrete geometry, geometric group theory are very algebraic and complex and geometric group are very abstract. They focus on really specific parts in geometry. And discrete geometry are mostly used in computer graphics or like a more problem solving. So like packings or like a lot more like graphs. Those are also discrete geometry. Famous theorems are Pythagorean theorem. Fermat's last theorem was partially solved with the help of geometry. And we also got Hodge conjecture, which I don't know what that is, but it's pretty famous, I think. Okay, some applications are relativity, art, computer graphics, string theory, calculus, complex analysis. The reason why complex analysis is so important because topology and some of the complex geometry and algebraic geometry provides a really good structure on how to model like complex graphs and like doing analysis on them. And also relativity and string theory uses geometry because relativity, as we know from Einstein, general relativity, space-time is not flat. It's a curve. There's a curve to space-time. So we use some of the non-Euclidean geometry and differential geometry to work out how space-times interact with like any other objects on it. And art as well, like M.C. Escher did a lot on symmetry, which is part of geometric group theory. And for that, I'm gonna put geometry in A tier. Although it's very important, but like I'm more about the math behind math and not. It's actually beautiful, like geometry, but in my opinion, it does not deserve the S tier. All right, algebra now. Algebra is the study of algebraic structures. So basically, some objects and their operations. So you have a bunch of objects and you have a bunch of operations. What can you do between the objects? So like interactions between them and what you get interesting. So basically what I've been doing is elementary algebra. So basically everything in A-level basically are elementary algebra. You just solve equations, you find solutions to equations. Linear algebra are just elementary algebra, but you have linear equations. So like the coefficients are just to 1, like x to the 1. And abstract algebra, which is just studying different algebraic structures. So that's more from a broader field rather than solving a certain equation. So like group theory, field theory, ring theory. Those are very examples of how they study different types of algebraic structures. Then we also got universal algebra and category theory, which is an even more broader and more abstract view of algebra. All right, some really famous things in algebra is fundamental theorem of algebra, Galois theory, and classification of simple finite groups. And that's group theory, and that's polynomials, and this is just also polynomials. So a bunch of applications are just solving equations, right? Like with physics, you have to solve something to find something. Like if you give me an equation, I can solve it with algebra. And also large language models use similar approaches because they use linear algebra, which are just very quick at solving for computers because it's linear. Quantum mechanics, game theory, geometry, number theory, calculus all use algebra. Basically, anything you do in math is algebra, right? You can't have math without algebra. Therefore, it deserves S2. All right, next, calculus. So calculus is just the study of continuous change. There's no more to that. So there's two parts in calculus, differential calculus and integral calculus. So changing like rates of change and accumulation of quantities. That's the most basic continuous change you can have. So some parts of calculus will include limits, infinitesimals, differentiation, integration, vector calculus, multivariable calculus. So some theorems are fundamental theorem of calculus, Green's theorems, and Fourier series. And some applications will be anything in physics, because everything in physics changes over time, basically. Half of it, right? Not quantum, but like the other half. So like basically Newtonian motion, Maxwell theory of electromagnetism, Einstein theory of relativity, economics as well, because money changes over time. Like that's just what you need in economics. And then nowadays, most mathematicians do dynamic systems instead of calculus and modeling. So this might be a bit controversial, but I'm going to put it in C2. I have a reason for this, all right? If you look back 50 years ago, it'll be probably A or S2. But right now, in my opinion, most of calculus is solved. Like, name me any scientist is just researching on calculus. Nobody's researching on the field of calculus. What they're doing is what I'm going to present next. And also, calculus, it's a tool, right? But the tool is pretty refined when we were like 1950s, where Raymond and like every other famous mathematician at that time basically come up with all of the set of things that you need to solve any generic calculus equation or like differential equation. Basically, if you give me a differential equation, there is probably a way of solving it. There's nothing unknown anymore, or like there's little, but like, nobody really is investigating all that. Most people are actually doing analysis nowadays, which is a small part. Calculus is just a small part of functional analysis, actually. It's studying how a function changes over time. But there's other things that you can analyze about a function, not just calculus. Calculus is just a really small part of analysis. And it's the extension of calculus, just like I said, after 1950s, where people will start getting bored because they finish with calculus. They start inventing new stuff and try to analyze different stuff, like numbers, complex numbers, functions, which calculus is part of it. You got harmonic analysis as well, which is signals and waves. That's where Fourier transforms comes from. Differential equations, which are partially linked to calculus, but they look at the relations between orders derivatives. So like third order derivative or like its derivatives and different orders right there. And then you also got measure theory, numerical analysis, vector analysis, tensor analysis, and a bunch more than right here. But all of these are just analyzing how we do math. That's the basic thing. So like, how do you use numbers? How are these numbers significant? How do these functions behave under certain criteria? Some of the famous things are just Fourier transforms, Laplace equations, Hilbert spaces, Taylor series, Rolle's theorem. And these basically analyze, or like these provide tools for analyzing different things like functions or numbers. So there's actually a lot of applications here: signal processing, quantum mechanics, Einstein field equations, Schrodinger equations. Because these are tools, they're so helpful in physics, because with the tools you have, you could basically try to learn more about the world, because you could use these tools and its properties of the functions that we already know to extract more information about them. Therefore, analysis is just better calculus. And in my opinion, it's good, but like maybe I'll move it up, but like it's about the top of B tier. That's what I think. All right, you can have your own opinion, but that's my opinion. All right, now we go to discrete math. Now, discrete math is just study of mathematical structures that can be described as countable sets, so integers. So usually what we do is continuous, but now we're just focusing on 1 and zeros. So anything that's countable infinity will be discrete math. So you got information theory, which is just quantifying information, so like sound or like images, and then that's very computer science. You got logic, set theory, combinatorics, graph theory, discrete calculus, discrete geometry. And then some of the most famous things in discrete mathematics is the four-color theorem, which just been proven like 20 years or 30 years ago, which states whether or not you could color a map with only 4 colors. And then you have Gödel's second incompleteness theorem, which is part of logic, where you can have something that is true. What is it? You can have something that is true, but unprovable or something. Yeah. All right. Then we also have P equals MP, which is another multi-million-dollar question if you answer that. And that's a good joke. But this basically means that can all solutions that could be easily verified be solved in polynomial time, basically. So if we solve that, basically we get like probably 200% better at anything. Because like traveling salesman problem is a really famous example. Basically, anything to do with transportation, if this was solved, it will be much more better. There's going to be no traffic jams at all. So some of the applications here would be optimization, computer science, cryptography, computer graphics, bioinformatics. And the reason why discrete math is also currently so good is because AI. Basically, everything in AI is built with zeros and ones. And that's basically discrete math. That's all discrete math. All right, so that's how significant it is. So I'll put it in A tier because I'm a computer scientist, right? So like I like math already, and I also like how algorithms and how do we think about algorithms and how this computer works. That's pretty linked into that as well. So next, we have logic, which is the study of formal logic with mathematics. It's really important because without logic, we can't do anything. Everything in math is based on logical like deductions. So we have set theory, model theory, recursion theory, and proof theory. So set theory and model theory are pretty self-explanatory. Set theory is just set theory, just looking at the basic, most fundamental blocks as sets. I'm going to come to that later on. Model theory is just how can we make a good model? Like, what do we need for a good model? Recursion theory is pretty interesting. It looks at like induction. How does induction work logically? And like, how does recursive stuff work? Like computation complexities. Like, let's say you have an algorithm that recurses itself. How do you know how good it is at doing something? That's what you do with logic. And also proof theory is like, how do you know that logical deductions are correct? Like, how do you know that we're making the like something that's correct? Like from one to like, how do we move from one step to another step without losing any generosity or studying about how can you contradict yourself with like proof by contradiction is pretty contradiction, like no pun intended, but like how can you prove something that's not true by just proving it can't be true? Like that's just contradiction. And you got some famous conjectures and theorems here. Completeness theorem, which is before we have logic, we thought like we could like sets could be complete or like because in the 19th century we have a paradox. I don't think is it here? It's not here, but I'm going to talk about it later in set theory. Basically, there's a paradox which means that you could have sets that shouldn't exist or contradict themselves, which then we lead up to like yeah, I'm going to talk about them in set theory later. But you have some what was it? I forgot their names, but it's a CT theorem, and then you got continuum hypotheses, axiom of choice, compactness theorem, halting problems, Fuzzy-Beaver problems are all logic problems. So like, how can we ensure that this is one of the methods of solving like one of the paradoxes later on I'm going to cover. Also, we got programming languages, philosophy, metaphysics, and computer science uses logic as well. So studying of how mathematical logic is constructed. And I think it's pretty interesting. So I put it in B tier because you can't, math is without logic is just nothing. It's just waffle. All right, set theory now. So set theory is just a branch of logic that studies sets, which are sets, which are collections of objects. So we got basically what they do is they look at the cardinality of sets and determinacy, axiom of choice, binary operations, and proper classes. Set theory, I'm not too sure about because I've never touched set theory before. So everything here is just what I've searched up on the internet. But this is what I'm talking about, the Sermilo Franklin set theory, is where they refurbish set theory. Before like 19 or like the 19th century, like set theory was pretty like basic. Nobody really cared. But then when they start asking questions about, oh, can we have some kind of set that's impossible, like literally impossible to create? Like, can you have a set with nothing in there? Then they just start contradiction. So they have to redo set theory again. And then there's the paradox here. It's one of the famous examples which led to having the Sermio Frankel set theory. And we also have general set theory, which is the one that it's the more modern version of Sermio's Frankel set theory. So some of the applications are equivalence and order relations of mathematical structures. This is really important. Basically, it means if both things are in the same set, then they're equivalent. And if it's a part of algebra and it's a part of geometry and they're basically equivalent, we could use what we know about algebra, we could use what we know about geometry, and then we could use them together to solve bigger problems. And one of the biggest things right now is the Lang problem or something. So basically, they're trying to connect more parts of math so that we could use what we already know and to solve other problems in some fields that we are not too sure about. And that's really important. MetaMaths as well. It's a program. It's like a thing that mathematicians trying to do to convert everything into set theory in set notation. Because basically everything is built from set theory. So like numbers, equations, everything could be simplified to set theory, which it's kind of absurd. But like, it's needed, but like it's a bit pointless. That's what I think. Topology in abstract algebra as well uses set theory. So in my opinion, I don't like set theory because although it's important, it's a bit it's like you don't have to look at math using set theory, right? Set theory is there, it's important, it's a fundamental, but it's not something to be analyzed, not something to be researched upon. Which, I mean, maybe you might disagree, but like I think researching on analysis or like algebra is more important than researching about sets, right? Let's go on to probability theory. So it's a study of events and numerical description of how likely they are to occur. So like, given an event A, how likely is it to occur, give a number. So some of the examples they do is sample spaces, independent events, mutually exclusive events, conditional probability, inverse probability. And you got all of these probability distributions, and then you got Markov chains and stochastic processes, which are all part of probability theory. And famous theorems are Cox theorem, central limit theorem, and I can't find any others, so that's probably it. And there's actually most of experimental science is built on probability and statistics. I'm going to come on to that later. So like actuarial science, modeling, LLMs, biology, quantum mechanics, all of them use probability. But in my opinion, it's a bit boring. So it's also in D2, unfortunately. All right, stats. I really hate stats. Just like I don't like it. It's required in basically any science. Like to do biology, you can't have you have to collect data. If not, you don't know whether or not your data is valid or not, or how to collect data. That's all statistics. So collecting, organizing, analyzing, interpreting, and presenting data is all statistics. But the only thing I love is the probability theory a bit. Because like, in order how do we like do math on such random variables, right? Usually, what you do is determining. Like everything you do in math it's already known. You can't have x plus 5 equals 2. X could only be negative 3. There's no randomness. But when you have randomness in there, it's pretty interesting how statisticians remove randomness from something in the world. Like the world is completely random. But I still think it's the way of doing statistics is pretty boring. But the math behind it is pretty interesting. But still, if we balance that all out, it's pretty bad. It's another D2. All right, game theory. This is interesting. All right, study of mathematical models and strategic interactions. So we got some examples of games, zero-sum, non-zero-sum games. So basically the difference between this is the total available resource are the same or different. So like let's say we have 100 apples and then we play a game. So at the end, it will be a total of 100 apples. There's nothing going to be added or subtracted from the game. but it's going to be the distribution of apples going to be different from different people, right? So this is really good to model like Earth resource, right? The resources in Earth is finite. There's nothing we can't add anything into it. We can't take away, but like we assume the taking away is just transferring the resources to some other places. And we got cooperative and non-cooperative games. So these are probably like investing or like making a company. So you study them with Nash equilibrium. So what's the best case scenario for both of them, or like for everyone to get the best case, we use Nash equilibriums. And then we got symmetric and asymmetric, simultaneous and sequential, perfect, imperfect, Bayesian, combinatorics, differential geometric games, evolution game theory. These are all game theory. So it's pretty interesting. It's pretty new field of math, actually. It's like probably around 100 years. And it's pretty significant in economics, because basically economics is about whether or not you get a better profit or they get a better profit. So it's pretty important when we do game theory. So famous things are prisoner dilemma, Stackman, Markov chains, min-max theorem. So I guess everyone knows prisoner dilemma, right? It's pretty famous about game theory. So applications are economics, political science, modeling, computer science, social science, biology, philosophy. So it's pretty social-based game theory, because it's about what's the best decision to make during a certain circumstance, or given an amount of stuff that we have to share or like to compete against. What's the best strategy? So in my opinion, I like game theory. It's pretty fun. So I'm gonna give it B tier, because it's pretty fun. Like I like having, because I'm also a board game fan. So like I like having different strategies and like doing math on which strategy is more optimal. All right, next we have combinatorics, study of counting stuff. So that's just counting. Everyone knows how to count, right? However, this is actually really hard. It's one of the hardest things in math. It's just to count stuff. So some examples are NCR, NPRs, enumeration. Those are called enumerations of stuff. So like how can you order them or organize them? And then you got existence of structures that satisfies given criteria. So that basically means how many things satisfy something. So like how many objects satisfy that, like how many objects, mathematical objects, could satisfy certain criteria. That's pretty important, because if we know how many there are, we could just try them out, or like we could just do some analysis on them. We also can construct different structures by using combinatorics. So like if we know that we have some objects that satisfy given criteria, we could use those and in combinations of them to create new stuff that has different criteria. And that's pretty interesting, because in the general, like if we do like algebra, like abstract algebra, we could come up with more like different operators by combining sets and stuff. And that's basically to do with combinatorics. Optimization, partition theory, graph theory, order theory, algebraic combination, combinatorics, geometric combinatorics, topologic combinatorics. All of them are combinatorics. So partition theory is pretty much what who is that? The Ramanujan, yeah. He did a lot on partition theory, which we don't know yet. It's basically how to count stuff. And also like four color problem comes up again, Ramsey theory and pigeonhole principle, which was the most important thing in math, basically, I'll argue. Computer science, dynamic systems, data analysis pretty much use combinatorics. But actually every other aspect, like most of math also use combinatorics. It's just that it's part of it already. Like it's so incorporated that you don't think about combinatorics when you do stuff, but it's actually part of combinatorics. Because the axiom of choice actually links back to combinatorics. To just choose stuff, it's a part of what we need to do math, like just choosing stuff. All right, so personally, I really like combinatorics. It's part of like, it's not as bad as set theory. Yeah, because it's important, but like it's already in everything else already. So like, it's just a two, but like at least it's like calculus. Calculus is also a two, right? You use it everywhere basically, but at the end, it's just counting. How good can it be, right? At least it's on par with calculus, right? So these are some of the bonus topics. I'm not going to talk about them, but I'm going to just slightly say what they are. So computer science is just, but everything here is ranked based on their math, right? Not how the subject is, right? So the math in computer science is basically discrete math and a bit of stuff. We got physics, we got astronomy, natural science, social science, economics, topology, information theory, system theory, operation research, group theory, and graph theory. These are the ones that are decided to rank them. And this is the end result. So physics, the reason why physics is such high is because they use a lot of calculus and everything else in math. Basically, everything in calculus is from physicists. Yeah? Because Newton invented calculus. And the only reason why calculus is needed is because of physics. That's why I think physics is going to be way higher than calculus, because calculus is just a tool. An actual thing, we will have the tool, but we don't know how to use it. There's no point, right? Because there's nothing interesting about calculus. It's just some small part about analysis, how a function works. All right, we got topology I like as well, but because the reason why I like topology is it's different. It's analyzing geometry in an algebraic way, basically. Computer science is with discrete math, of course, because they're both basically the same thing. System theory is pretty interesting, but I'm not going to go into it because we don't have much time. Graph theory is about computer science, but basically the same. We got information theory, which is also computer science, but I put it a bit lower because I don't know much about it. Group theory, it's pretty interesting. It's part of logic and algebra, and it's also part of like how different groups behave, which I find interesting. Operation research, economics, astronomy, those I put in C tier because they're more mathy than natural science and social science. Which I mean, there's a bit of math, but like I wouldn't say they're really mathy. All right, but now for the end, you can scan this QR code, and I'm gonna get some data, and I'm gonna report back maybe in next week or the week after. All right, thank you for your presentation or my presentation.